All right, in the last video, we talked about matrix similarity. And in this video, we're going to see what diagonalization means and an easy example of how to compute the diagonalization of a matrix. So let's write down a definition. So we're going to start with an n by n matrix A and another n by n matrix P and D an n by n diagonal matrix. Now, if we're able to compute and verify that A is equal to P times D times P inverse, then we say that that PD P inverse is a diagonalization of A. And if such a P and D exists for a matrix A, we say A is diagonalizable. Another way of saying that is that A is similar to a diagonal matrix. It turns out there's some really nifty things about diagonalizable matrices and, in fact, how we can find a D and a P that will work for a given matrix. So one of those facts is that a matrix A is diagonalizable if and only if we can find n linearly independent eigenvectors. And when it is the case that a matrix has n linearly independent eigenvectors, and this is of course an n by n matrix, then we actually have P and D already figured out for us. Because it turns out that what will work is diagonal matrix D that has the eigenvalues of A along its diagonal and zeros everywhere else. And the matrix P can be taken as just the matrix with column vectors equal to the corresponding eigenvectors. So it's important that we write them in the same order. So whatever vector is paired with lambda 1 needs to be the first column. And whatever eigenvector is paired with lambda sub n needs to be the nth column, and everything in between, right? The eigenpairs have to exactly line up. So this matrix D, which is a really simple diagonal matrix full of eigenvalues, has the same rank and nullity and the same eigenvalues, of course, as A. So let's see an example of how to diagonalize a matrix, right? And when I say that, I mean, how do we find the diagonalization of a given matrix? Okay, so let's diagonalize the matrix A, provided that we can find two linearly independent eigenvectors. We just need a matrix with eigenvalues down the diagonal, and then the matrix P is just going to be the eigenvectors listed in the corresponding order as columns. So that means we're going to have to find the eigenvalues. So step one is find the eigenvalues of A. And to do that, remember, we're going to compute the determinant of A minus lambda I and set it equal to 0. And then we have to solve that, in this case, a quadratic equation. So we've got the determinant of A minus lambda I is the determinant of 3 minus lambda, 2, 4, minus 4 minus lambda. And this comes out to be, let's see, it's 3 minus lambda, minus 4 minus lambda, minus 8. We're setting this equal to 0 and solving, and if you work out the algebra, you'll get lambda plus 5 times lambda minus 4 as the factorization. So our eigenvalues are lambda equals minus 5. I'll call that one lambda 1, and lambda 2 is 4. So that is step one, finding the eigenvalues, and then we need to find the corresponding eigenvectors. So we have our D already. Now we just need to find our matrix P by finding the eigenvectors. So let's just start with lambda equals negative 5. So to find the eigenvector for lambda equals negative 5, we have to solve this homogeneous linear system. You can see that if we do one row operation, we're going to get the matrix 8, 2, 0, 0 times our v1 vector is equal to the 0 vector. And if I write down the general solution for this, it's going to say that my first component is equal to 1/4 of my second component. So we can take as our eigenvector, which we're only interested in to specify the direction as, let's see, we could take 4 as the second component so that 1 can be the first component, and then we have nice whole numbers. And keep in mind that it doesn't matter exactly which vector we pick, it just has to satisfy this. So that's the general solution to the homogeneous system. We just have to pick any vector that's pointed in that direction. So I will pick v1 equal to 1, 4. And now I have my eigenvector that's associated with eigenvalue -5. Now let's find the eigenvector that is going to be associated with lambda 2 equal to 4. Okay, so finding the eigenvector associated with eigenvalue 4 requires solving this homogeneous system where I've just plugged in 4 for lambda. And if I solve this, I'll see that the first component is equal to 2 times the second component. And that's my general solution, but I only need one particular solution to write down as my eigenvector. So this is the general solution. In both of these cases, v2 is free, but I'm going to take any vector that points in that direction. So I'll pick v2 to be 1, and then v1 is 2. Now we have our 2 eigenpairs for this 2 by 2 matrix, so we can write down the diagonalization. So A, our original matrix, is equal to P times the diagonal matrix with the eigenvalues along the diagonal times P inverse, which I got just by computing the inverse of P in the standard way. So now even if I wanted to compute A to the 100th power, I would still only require n exponentiations to get the values of these diagonal entries for D to the 100th, and then just 2 matrix products. Right? So A to the 100th is equal to P times -5 to the 100th, 0, 0, 4 to the 100th, times P inverse. Right? And so instead of 99 matrix multiplications, I only need to do 2, which is a really big savings in terms of computational time. Okay, so that's diagonalization. In the next video, I'll show a more complicated example where we run into repeated eigenvalue and how to deal with that.